Hello, everyone. I'm Yung Wang. Welcome to the session of Software Process, Software Engineering Education. The following starts the first presentation. The authors have already informed us that his network is not good and it is not easy to get stuck online. So we will play the pre-recorded video. Dr. Yang, please play the video. Hello? Can you hear? Okay. The first presentation title is structural similarity. Okay. Hello, Dr. Yang. Dr. Yang. Cannot hear the sound.
Maybe you can play from your side.
Yeah. Okay.
Sure.
Please wait for a minute. I'm sorry. Okay. Waiting for a minute. I will play the video in my computer.
Two of this specification are PC1 and PC2. PC1 captures the situation that high water and machine will happen in the future. PC2 captures the situation that high internet and machine always happen. Under the PC1 or PC2, two goals are unsatisfiable as a whole within domain quality. Now, we give a formula definition of BC. Given domain quantities and goals, it's called a quantity. Logical inconsistency means that the conjunction of goals becomes inconsistent when the BC holds. The minimality is mechanically one of the goals no longer results in the inconsistency. The non-purity forbidden of BC to be a true condition, which is a negation of the conjunction of the word, which is the negation of the conjunction of the words. Intuitively, BC captures the situation where the goals as a whole are not satisfied. And then, we are going to give you an idea of general BC. Given two boundary conditions BC1 and BC2, we call BC1 is more general weaker than BC2. If BC1 and if BC2 implies BC1, for example, in Martini, we say BC1 is more general than BC2 because BC2 implies BC1. We would define one general BC because once it is worked out, less general BC will also be worked out. There are two challenges in low conflict identification. One is how to identify the BC in time. The other is how to identify all general BC. We found an interesting phenomenon that there exists some pairs of BCs which are similar on the structure. For example, in part 1, BC1 and BC2 differ in only one operator. If this phenomenon is common, then one of BCs is covered. The other may be found or simply change the form. The question is, how frequently similar BC pairs do occur in case? We think BC as syntax tree. For example, and use tree ID distance to measure the distance between the two BCs. We also use bit theorem as normalized tree ID distance. And we define two index. The sum of BC means that similar means that the percentage number of similar pieces. We use these two indexes to separate the pieces out by existing algorithm. We generate pieces by applying the root and GA-based approach. More than 70% of PC have more than one EC nearby. The results using the normalized are similar to the first one. And the percentage minimum between most similar PCs is less than 2. So, we say that PC pairs with similar structure are common in different cases. We design a local search algorithm. Okay. We use the structural similarity of PCs to identify PCs. The key to LOGION is the neighborhood function. We first to design 3 LTL formatted operators to slightly modify an LTL format to another LTL format. We need a single insert an operator, edit an operator. The neighborhood function is all function obtained by applying a formula adding operation to a subformula of phi. The initialization means detection of congestion we use the objective formula mentioned by it means in each iteration, we compute the set of papers of the correct move to the papers and practice the DC papers. So we have to ask to what extent LOGION describes the structural similarity of PCs. The table shows DCI plus 1 means that the longest distance between DCI and his SDCI plus 1. The DCI is similar. In other words, it's possible that new PC may be found then compare the performance of LOGION with the state. Metrics in the the advantage number to sum up our work. First, we discovered an interesting phenomenon that there are some pairs of DC and similar in formula structure. Second, using this phenomenon, we propose an efficient research mechanism named LOGION for low conflict identification. In the future, we hope to optimize the DC verification procedure by reducing the cost of the LPR sensitivity checker. Thank you for listening.
Hello, everyone. If you have any questions, please contact the authors by them emails. Okay. I have already closed the science screen. We will move to the next presentation. Here, Noriko, are you ready? Noriko,
Yes,
are you ready?
I can.
Please start your slides. Okay, I can your slides.
Can you hear me? Just a moment.
Yes. Okay. Yes.
Just a moment.
Yes. Yes.
Can you hear me? Just a moment. Just a moment.
Yeah, okay.
Just a moment.
No problem. Okay.
Let's start. Can you hear me?
Yes.
Can you hear me?
Okay. Okay.
Okay, so let's start. Today I'd like to talk about education model for project-based learning using ability map in various target products. I am Noriko Hanakawa from Japan. So, PBL, project-based learning program, PBL, project-based learning, is a popular education method in software engineering. Just a moment. However, there are several problems. First, a difficulty of individual student evaluation in team activities because various final product and teacher have to watch carefully behavior of individual student. And next, disparate to make program. Teachers and students mainly focus on programming activities because programming is exciting and indispensable. Teachers and students may require the full class time allotted to complete the program because PBL classes do not have sufficient time. Then students may acquire few project management skills, communication ability among students. These are PBL problems. Therefore, we propose an educational model for PBL using ability map in various target projects. This is our proposed education model for PBL. Using the proposed model, even if the final product are various. For example, Team A's product is business web application. Team B's product is IoT sensor system. Team C is a programmable drone. The individual student can be fairly evaluated with not only programming skill but also management ability. So this is the today's content. At first, I explain an educational model for PBL. Next, I show empirical adaptation of the model and discussion summary. At first, I explain an education model for PBL. This is the model concept. So the proposed education model for PBL is a general model including three meta models. First meta model is a resource pyramid meta model. Second meta model is an educational process meta model. Third meta model is an ability mapping meta model. This is a general model. Then a PBL class start. A teacher prepare a implemented model for each project. For example, in Team A, business web application PBL model. Team B, IoT sensor system PBL model. Team C, projection mapping system PBL model. So this is, we call them implement model for each project. Next, I explain three meta models. The first meta model is a resource pyramid meta model. The resource pyramid meta model defines role of teams. The top of the pyramid is a professor who has all responsibility. Basically, students start as a novice member, like this. Students grow up an experienced member, and next team leader, and next a full leader, like this. The timing of the changing role is when one project finishes. Basically, the period of one project is half a year. If PBL curriculum is during 2 years, students will have a chance to participate 4 times project. And next meta model is an education process meta model. These are the education process meta model presents the actions of PBL education actions. The process model consists of 6 phases: planning, analysis, design, implement, integration, running, and 24 tasks. For example, first meeting, collecting material, field investigation, and so on. Of course, The phases and tasks can be adaptable to various projects. The final product are web application, IoT sensor system, and drone programming. And the last meta model is an ability mapping meta model. So ability mapping meta model shows assignment of all tasks to roles of human resource pyramid model. This is a ability mapping meta model. So these are phase and task. So in the education process meta model, this is the phase name, this is a task name. And this column means roles of the resource pyramid meta model. For example, team leader and check mark means assignment of the task to the role. For example, a team leader have to do task 2 like this, and task 2 required ability 3, ability 4 like this. The required ability to complete the task. General ability such as organizing the requirement. In the ability mapping meta model, ability are defined. Abilities are defined like this. And next, product column. The product column is blank at the meta model. Because the product name are determined in the implemented model of each project. For example, class diagram or Java source code. So in the meta model, product column are blank. This is an ability mapping model. Basically, the three meta models are based on the past PBL education result from 2012 to 2016. Next, I show empirical adaptation of the model. From here, we show the adaptation of the model. First, configuration of PBL practicum classes. And second, creating implementation model for PBL practicum classes. And the third, results of PBL practicum classes in practice. At first, I explain configuration of PBL classes. The PBL practicum classes are set to 2 years. 1 year has 2 terms. One project basically is completed during 1 term. Therefore, a student has a chance to join 4 projects. This is first year, first term, second term. Second year, first term, second term. So for example, at the first year, first term of first year, student A join as a novice member. And at the second term of the first year, student joined as experienced member. And third, first term of second year, the student A joins as team leader. And at last, student A joins as pole leader, last term, like this. So student A grows up from novice member to a pole leader with sufficient knowledge and experience, like this. And next, creating implemented model for PBL practical classes. This is a general education model, including 3 meta models. So a teacher makes an implemented model based on the 3 meta model. A target project is a restaurant reservation web application. So in the human resource pyramid model, the professor is teacher A. Whole team leader is a student 1, and also team leader also student 1. And the experienced team member is a student 2, 3, 4, 5, and the novice member student 6, 7. So a teacher are assigned to student to the roles. And next, the teacher designed the lecture of the PBL. The first lecture, lecture 1, planning phase. First meeting on collecting materials, activities. And the second lecture, analysis phase, making the system scenario and so on. Lecture 3, design phase, design of the divided scenario and so on. And the lecture 4, implemented phase, implemented system, a program like this. And based on the ability mapping meta model, so teacher set concrete product like this. So for example, design phase and design of a divided scenario task. So product are flowchart and module structure and data table. This is a teacher set the product. So this is a teacher make an implemented model. So next, result PBL practicum classes in practice. A case of student 2. Student 2 was assigned to the team member in the project. So the student 2 make flowchart, module structure, and data table like this. So teacher check the completion rate of the each product. For example, flowchart completion rate is 80%, and module structure and data table is completion rate is 70%. And next, calculating score of ability like this. So this ability score is 3.0 based on 2 completion rate. And the student 2 score is average of these score of the activities. For example, in this case, 2.4 is student 2's score. In this case, maximum value is 3.0, like this. So this is a student 2's score. Discussion. At first, I discussed United Evaluation criteria for various target products. Second, 2 years PBL practicum classes are difficult. At first, I explained United Evaluation criteria for various target products. So if the PBL education is based on the proposed education model, the student will be fair evaluated, even if the final product varies. This is a web application. This is a projection mapping system. This is a dynamic memory change system. The final product varies. we can provide the united evaluation criteria for various final products. And next discussion is 2-year PBL practical classes are very difficult. The PBL education starts from 2019 at the second term of 2019. So 4 projects were concurrently active. Therefore, if one teacher has to control the 4 projects, the workload of the teacher will be very heavy. Because we can provide the united evaluation criteria for various projects, the other teacher can be assigned to the other project. The assigned teacher can be freely set projects based on their specialty product. So summary, we propose an education model for PBL with 3 meta models. The education model was empirically adapted to the PBL practical classes. As a result, we can provide the united evaluated criteria even if the final product evolves. In future, we will refine the education model. Thank you.
Hello, thank you. It's a very interesting topic. Any questions?
Sorry, I can hear your voice.
Okay, can you hear me? Okay. Yeah. Any questions? Okay. I have a question. It's a very interesting topic.
Yes.
My question is, in the education model, the ability map is important. But how to ensure the rationality of ability map? How to ensure the rationality, the ability map? Okay.
Rationality. Sorry, just a moment.
You can see the message. I give the message in Zhong.
Okay. I see. Ability map. Ability map. Okay. Sorry, I can't hear you. So ability map is here. It's very important. I think so.
Yes. Okay. Okay, thank you.
Thank you.
Thank you. Okay, Noriko. We have the next presentation. Hello. Erina. Hello, Erina, are you ready?
Okay, I try to start my presentation.
Yeah. Okay.
So can you see my slide?
Yes.
Okay,
Yes,
thank
I
you.
can.
Thank you. So I'd like to start my presentation. So hello everyone. My name is Erina Makihara. I belong to Dosha University in Japan. Today I'd like to have my presentation. The title is Understanding Video Art in Agile Software Development Project-Based Learning. So first is the background that the demand of teaching students practical software development skills are gaining significant attention. So the practical software development skill does not only refer to programming skill, but also the ability to communication, to identify problems, and propose solutions independently. So various institutions have been conducting advanced programming education aiming at experiencing software development in the form of project-based learning, with courses such as experience style as STPBL. Lately, the Agile software development model is often applied in STPBL. Then the many previous studies mention that the build is regarded as a core step in software development. Then in software development, build is the process of taking all source files that constitute an application and compiling them into binaries or executables. Then Agile model requires developers to repeatedly perform the cycle of plan, implementation, test, build at regular intervals. Then, but there are some problems that the finding build error incurs significant cost for enterprises such as Google or Microsoft, because the errors occurring in the build process are not only due to lack of programming skill, but also non-technical skills such as human factors lacking the bad team communication or bad team communication or knowledge sharing. In software development education, it is critical to identify the build errors commonly made by students, along with the causes and appropriate effort needed to fix the errors. However, a large empirical study on the build process in software development exercise in the field of software engineering education has not been conducted yet. So, our research purpose and the approach is that we investigated when and how students cause build errors by monitoring their build behavior in STPBL from 2013 to 2016. So in our development environment for STPBL, students are required to build locally and then commit to the team version control system. In the version control system, Jenkins build and test their source code automatically for each commit. We call the build logs collected by each student build in their own local environment as local build logs, and we call the build logs collected by any team members commit in team version control system repository as remote build logs. We analyzed two build logs collected from 2030 to 2050 to answer the following research questions. Those research questions are based on previous research by Xiao. He investigated the build error logs in Google. And then in 2016, we considered to provide frequent feedback of build errors to students based on the results from 2030 to 2050. Finally, in 2016, we analyzed the local and remote build logs to answer the same research question to compare with previous years. Then I'd like to explain the investigation target and investigation target STPBL project. So, investigation target project is named as Cloud Spiral. Cloud Spiral is a national educational program, and our target STPBL is conducted as a part of Cloud Spiral curriculum. So all Cloud Spiral participating students are first year master students, and they major in information science field. The STPBL consists of 1 day for preparation and 4 days hackathon style. And the target STPBL require students to develop a web application or ticket purchase system in team consisting of 5 or 6 students using an agile development method and ticket-driven development. The scale of target system is the target system includes 13 functions, and by the end of the hackathon, the average LOC of the target project is approximately 6,000 lines, and the number of files is approximately 100 files. And then all the specifications and development environment are provided to the students by the instructors. So each team implements a web application based on the common specification, but which is able to determine the order of and the role of implementation of functions. Then I'd like to show the result of each research question. The table shows the number of build logs, not only failure log, but also success logs from 2030 to 2050. After we collect the finishing SCPBL, we focus on the failure build logs in both of local builds and remote builds. Then I'd like to show the result in 2030 to 2050 of RQ1. RQ1 is which types of build error occurred. So we categorize the build errors collected from the SCPBL logs by using the categories proposed by Xiao at Google Research. So the left categories are defined by Xiao, and we add 2 new types of build errors, annotation error and environment error. The target SCPBL used Java Bean validation function, so there are many build errors regarding validation. So we define the annotation error category. Annotation error includes error due to the improper use of annotation. And we also define the environment build errors. So environment errors include error due to the development tool used in SCPBL as belonging to the environment. However, environment errors are mostly caused by development environment or tools, but which are mostly prepared by the instructors. So we omit the environment data from the following results because we do not regard the environment errors as a target of our investigation. Then, so I'd like to show you a result of RQ2. RQ2 is what is the frequency of occurrence of each type of build errors. So the table shows that the number of build errors of each 6 categories. All year remote build more than local build errors. And the greatest number of build error in remote is dependency error, and the result is the same with SEO research in Google. So we consider that the dependency error as one of the characteristics of team development. And then we investigate those build logs more detailed. So I'd like to explain that. First, we investigated how dependency error occurred. Then we found that the main cause of this error was that the source code of unit test committed to the team repository without a target program. For example, there are student A and student B in a team. Student A implements the test file, and the target file is implemented by the other student B. Such situation, sometimes student A implements the test file and also the target file in his own local environment, but student A did not commit both files. Student A only commits the test file, and then the test file is frequently committed to the version control system team repository before the target file is not committed. So the Jenkins output cannot find symbol build error. So such situation, student A cannot prevent the build error by himself. So it is important that all the team members have a detailed understanding of each member's task and progress before each commit. Next, we investigate the build error log by classification. The vertical axis represents the number of build errors, and horizontal represents the students in a team respectively. The upper half of the figure shows the number of remote build errors, and lower shows the local build errors. We focused on the student who occurs such syntax error. The color is blue one. Then we found that the students with syntax error in their remote build do not encounter any syntax error in their local build. On the other hand, the students who cause the syntax error in local build, they do not cause the syntax error in their remote build. So we assume that syntax error are able to prevent from occurring in team version control system repository by slowly checking one student's self-review and local build. And finally, we investigate the build error logs by time series transition. So we focus on annotation error. Almost all annotation error occurred in pre-sprint or first sprint. So we assume that the main cause of annotation error appears to be that students are unfamiliar with annotation. So we think that by improving students' skill and knowledge of annotation, students may be able to reduce annotation error in team remote repository. And next is the result of RQ3. RQ3 is how long does it take to fix each type of build errors. So the figure shows the resolution time by each error type in 2030 to 2050. So each type of error, the resolution time for local and remote build are indicated by the box plot on the left and right respectively. Then, except for type mismatch and semantic, the resolution time in remote build was longer than for local build. And we found that by committing source code with bugs by a member of a team, it spreads the defective source code to other team members. And we define such error type as mix error. So mix error category on the right-hand side includes errors that require the resolution of multiple types of build errors. And almost all types of build errors in remote build, the mix errors require the longest time to be resolved. So we assume that it is high risk to commit defective source code to team version control system repository, and it also high risk to ignore the build errors in remote environment. Then the STPBL instructors improved the STPBL in 2060. So before the STPBL in 2060, instructors explained the main causes of each type of build error, as well as the importance of local build to students. And instructors also explained that the resolution time becomes longer and bugs are spread if students neglect to fix multiple errors in remote build. And each sprint, the instructor requires members of each team to investigate the cause of each remote build error that occurring during the sprint. And finally, after the above mentioned investigation by students, the instructor determined whether each error was caused by the lack of local environment or lack of team communication and provide feedback to each team. And then I'd like to show the result in 2016 compared to previous years based on RQ. So the RQ1 and RQ2 in 2016 years, the most of local build errors occurs than previous years, and the least remote build errors occurs than previous years. And we investigate the detail. The number of local builds was the largest during the press sprint of 2060. So this indicates that in 2060, students generally have sufficient experience of build and build error before starting the hackathon. The result means that instruction of build error in the early phase is important to ensure that students comprehend the build activities. And next is the result of RQ3 in 2060. The left figure is resolution time by each error type in 2030 to 2050, and the right one is 2060. However, the number of target logs are different, but in 2060, almost all resolution time by each error are shorter than previous years, and the number of mixed error was reduced in 2060. So in remote, the mixed error in remote is 0 in 2060. So we assume that providing students with instruction on the occurrence of mixed remote build errors as a result of splitting bugs alerts students the consequences of introducing the errors and also help students to reduce the resolution time of build errors. So that is the conclusion that we focused on build errors and analyzed it during the STPBL from 2030 to 2050 based on the RQ. The result of our investigation shows that the cause of remote build errors are related to both technical factors and communication among students in a team. And also we improved the STPB and TD60. The result shows that the number of remote build errors that occurred in each team significantly decreased, and that is the resolution time becomes shorter than in the previous year. So our future work, we are planning to develop a we are planning the PBA support system that analyzes both of local and remote build in real time and provides the result to students and feedback. So that's all of my presentation. Thank you for your attention.
Okay, thank you.
Thank you.
Any questions? Yeah, any questions? Yeah. Why are two new types of building errors added? Why?
So you mean the reason why those annotation error and environmental error? So in previous research, actually annotation error includes a semantics error in previous research, but the target project uses the beam validation, so the build errors regard annotation is much occurred in our STPBA, so we extract the types of errors and investigate the reason why such error is occurred. So, can I answer the question?
Okay, okay. Thank you. Thank you.
Thank you very much.
Yeah. Please close your shining slide. we move to next presentation.
Okay, so thank you very much.
Thank you. This, okay. We start the next presentation. Hello, Antonia.
Hey, how are you?
Hello, how are you? Okay.
Everything's good. I'm gonna share my presentation, see if it works. Can you see this?
Okay.
Can you see my screen?
Yeah.
Okay.
Yes.
I'm gonna start then. Yes, hi everyone. Thank you for being here. Of course, we would have loved to be in Singapore to present our paper, but we all know what happened. I'm Antonio Martini. I'm associate professor at the University of Oslo in Norway. Now it's 8 o'clock and it's very dark outside, but my screen is very bright. So I'm Antonio Martini. We did this paper together with Terese, Besker and Bosch from Chalmers University of Technology. And this was done in collaboration with Software Center, which is a consortium of companies and academia and universities, I mean. And there are different projects, and one of these is on managing technical debt. And also we try to explore what process debt is with some companies in the north part of Europe. So this is where this study comes from. Let's start with some motivation. So why should we study process debt? Why is that important? So process debt, we know that we have process improvements that need to be prioritized with respect to other issues. Like we have to prioritize basically everything: features, bug fix, technical debt, process improvement, social issues, and so on and so forth. But our backlog is usually limited, so we don't have that much space. Like in this case, we have like 3 slots for the next sprint, let's say, and we need to decide what to prioritize. And also we know that different people, basically different roles, they tend to prioritize different things, right, to put in the backlog. So what happens? We know from previous research that technical debt is generated by down-prioritized technical issue, right? So if we don't put technical debt into our backlog, we are gonna keep technical debt, and that's gonna hurt in the future. So the idea here is, our process improvement also down-prioritized the same way as sometimes happens with technical issues? And then, if that's true, do we actually have something like process debt? We looked a little bit into the literature. We didn't really find that much related to this problem. So we try to understand if actually the metaphor of technical debt can be used to also manage process debt. I give an example of process debt. So maybe otherwise it becomes a bit too abstract. One example can be the lack of synchronization between agile process and a certification process. Imagine if you have like an agile process with continuous delivery, and teams that they continuously deliver value to a company or to their customers. But we also have a certification process, which is let's say another process that is not synchronized with agile. And at some point we need certification documentation, right? We need to prove that for example, for a safety critical car, we need to provide like certification, a documentation. But the team actually don't know this because this process is not well integrated or synchronized with the agile process. So they arrive here and now suddenly they have to provide a lot of documentation, and that's not exactly what they expect. So they have to stop delivering value, and they just have to create a lot of this documentation. And this can be a problem because you can have confusion and frustration from both sides, both from the teams and for the certification team or stakeholders. We can have lack of important documentation because maybe we didn't, the team didn't prepare that timely. And then there can be a lack of flexibility for the teams because once they arrive here and we need to do all this documentation, we need to stop delivering new software, but we just need to do documentation. So there are several problems in this, synchronization issue. So this is an example of process debt, because we have a process that is not well integrated, and we have a consequence that we call it interest in technical debt community, which means it's the extra cost that we pay when we accumulate a suboptimal solution. This suboptimal process causes this sort of interest on the side if it's not fixed. So this is an example. What are our research questions? First of all, we try to understand how to define process debt, what type of process debt do exist, how process debt is accumulated over time, who is responsible and how does it happen, what are the causes, what are the consequences, and if there are similarities or differences between process and technical debt, because technical debt has been studied quite extensively in the last 10 years. So maybe if we have good practices, we can actually use them to tackle process debt. So that's the idea. What about the study design? We have 3 phases. The first one, we actually did a workshop. We did some contextual analysis and design. So we reached out to the companies. We tried to understand if they have, try to understand if they have instances of process debt. We try to understand if this is something that could fit. And we try to elicit cases that we could analyze about process debt. So it was to understand if we could actually do the study. Then we understood that this was actually a good opportunity to do the study. The companies were interested and they actually have some cases. So we actually did some qualitative collection. We had semi-structured interviews. We looked at documents about cases of process debt, and we also had some unstructured interviews as well. So the idea was to be very open and try to explore this topic to try to understand what process debt is. And then we had analysis and synthesis, and we tried to make sense of all the data that we collected and try to create a framework and a definition for process debt to understand the whole phenomenon. So how did we do the data collection and analysis? We had 4 large companies, 16 participants. As I said, it was very open-ended questions, semi-structured and even unstructured interviews. So we wanted them to describe examples of process debt, looking at process documents. And we did a data analysis. So we had like explanation building. As you can see, we had some sort of mind map where we had different codes. We coded the data in a similar way as you would expect for a qualitative study, similar to a grounded theory. Although here we didn't really reach a theory because you need a lot of more probably data. But it was done in a similar fashion, and this is basically what we have been doing. So what are the results of this investigation? I'm going to go through quickly because we don't have a lot of time, but I will just stop to describe maybe a couple of the most interesting things. So research question 2, I'm starting from research question 2 about process debt types. So the first thing which is interesting is that process is consisted of several activities, and each of these activities can be suboptimal. And in that case, for example, if you have a whole process of which part of it is an activity on prioritization, and prioritization is not, it's suboptimal, then you have prioritization debt. Even though the whole process can be suboptimal, but if the prioritization activities is suboptimal, then you have prioritization debt. So if you have all these activities, or unit testing or other kinds of part of the process that can be suboptimal, then we have a debt that is named after that activity. Then we have roles. We might have roles that are not well fit. Documentation debt, similar in what documentation that is in coding. As I mentioned, might be that the processes are not well synchronized. Process can be not suitable for the purpose. And also we found infrastructure debt. I think this is interesting because we know that infrastructure is actually there to support the process. And if that is suboptimal, this can actually be a big hinder for a big boost for process debt to have suboptimalities in the process. So infrastructure in this case is very part of the process debt problem. We have a lot of causes as well. Again, I'm not going to go through all of them, but I'm just mentioning some of them. For example, value neglection. This is an interesting one. A lot of the processes that is accumulated because the value is not understood by the ones who execute the process about what value the stakeholders get out of the process. Other problems can be cultural factors. We actually found a lot of cultural issues that cause process debt, and we found that some of the interviewees actually mentioned that this could actually account for even half of the process debt that is created. And in general, we can see that cultural factors come down to experience, maturity, motivation, leadership style, and several others. There are other ones, organizational factors. We also found quite a lot of organizational factors, and it can be different culture, different interests, power balance, and so on. And we have this interesting one, external trends. Sometimes we get process debt because we have an external trend of a new process. We want to try it, but it doesn't really fit. So there are a lot of causes. I suggest you to read the paper if you're interested in some of them. We also found a lot of consequences of process debt. We know that actually some consequences include some initial waste, which usually are suffered by developers. So we can have developer overload, developer mistakes, developers morale, and so on and so forth. And this is one that is quite important. It's the loss of trust in the process, because if developers or the executors feels that the process is not good, then they accumulate even more process debt. We have also the long-term one, and I think one of the most important here and interesting is that we found that a lot of process debt actually creates technical debt. So we have a lot of we have a lot of research now on technical debt based on trying to tackle the technical debt problem, but actually we know that process debt is one of the main causes. So if one could try to fix process debt, then maybe some technical debt is also automatically avoided. An interesting thing is that this initial waste, if it's overlooked or it's not well managed, it can become long-term issues. So this is a bit special about process debt. So this is the overall idea about process debt. This is our framework. And we start from one side. We know that stakeholders, let's say, give input for getting an optimal process. This optimal process is subject to these three accumulation patterns. And here is research question 3 about how technical process debt is accumulated. And you can see there are 3 different ways. There is a divergence from an optimal and formal process, but it can also be that the formal process is actually not well designed. And those are 2 different accumulation patterns. Because if we have an optimal process, the executors might diverge. But if the starting point is already suboptimal, then that's the actual issue, process debt. And then as we mentioned, there is also suboptimal infrastructure. We showed the causes before, and also there are several initiators. So it can be the process designer, the process executor, or the infrastructure itself that actually starts the accumulation of suboptimality. There are a lot of consequences. We discussed this. There are different types. We discussed this. And then how can we assess process debt? And here we have two variables that we actually know from technical debt, which are actually valid here for process debt as well. One is the cost of change, which is the principal. It's called the principal in technical debt, which is the cost of fixing the debt. And there is the negative effects that are actually the interest of the debt. The new one, I would say that we didn't really find that much into the technical debt community is the value for the stakeholders, which is important to understand about process debt. If we calculate these 3 or we try to assess them, then hopefully we get a better prioritization of process improvement. So this is the whole idea about process debt. We try to understand, assess, and get better at prioritize. We also have a new definition, which is part of our answer for research question 1. It's similar to the definition that we get from technical debt about the Dutch tool seminar. But of course, the actual debt is different. And also we added this short-term waste that is a bit special about process debt. Finally, we want to understand the differences between process and technical debt, research question 6. We found some similarities and we can find some differences. We see that the way in which the debt is accumulated is similar. So we have a short-term focus leading to long-term consequences. That's something that it's similar for both. But there is a difference. Process debt also generates this initial waste, like I mentioned. About variables to assess the debt, like I mentioned, principal and interest variables are similar, meaning that we can use it for process debt assessment. The value is something a bit newer for process debt, because it's not so obvious that the process actually gives some value and the value of the process decreases over time. While if you think about the code, it's more obvious that you need the product to give it to the customer. So the value is not something that can be there or not, or it's a bit more, let's say, obvious, the value. But for the process, sometimes you might have a process that it's not obviously, it's not obviously valuable. So the value is a key difference here. About the causes, we found similar suboptimal, we found similarities. The suboptimal prioritization is a common cause. Both process and technical debt are overlooked because they're not prioritized. Process and architectural debt are similar. There is a design and an execution, and in that sense, we have two different patterns of accumulation. One is the design that is flawed, and the other one is that the design is optimal, but the execution is flawed. That's a similarity with architecture. Other consequences, the difference is we understood that in the process, there is more emphasis on continuous disturbance for stakeholders for process debt, which is a bit different from technical debt. Measures, we found that process that is less measurable, and we also found the process that needs additional prioritization, additional categorization about, this is a typo, additional categorization. So we have all these activities and we need to categorize better. And then we found the last one is that documentation is similar for architectural requirement documentation, but there's no code documentation there. So conclusions, process debt is harmful, but we didn't find that much research. So this is the first step. We define process debt, we provide a first framework for reference, but more studies are needed to further understand this process debt. So we hope that more will jump into this and help us uncovering the process debt. And process debt is similar to technical debt, but has key differences. Some techniques can be adopted, but new practices are needed. That's it. Thank you very much for listening.